John Roebling never saw a single cable strung across the East River. He designed the Brooklyn Bridge. He chose the site. He developed the wire cable suspension system that made a span of that length possible. He spent 20 years advocating for the project before the state of New York authorized it in 1869. 3 weeks after ground was broken, a ferryboat crushed his right foot against a dock piling while he was conducting a survey on the Brooklyn waterfront. The foot was amputated. He refused further medical treatment, insisting on hydrotherapy, a water cure regimen he believed in over the objections of his physicians. He developed tetanus. He died on July 22, 1869, 63 years old, having never seen the project he had spent his career designing begin in any meaningful way. His son, Washington Roebling, took over as chief engineer. Washington was 32 years old, a trained engineer who had worked alongside his father for years, and who understood the bridge design at the level of someone who had helped develop it. He would direct the construction for 14 years. By the end of those 14 years, Washington Roebling had not stood on the bridge site in over a decade. He had directed the final years of construction from a window of his house in Brooklyn Heights, watching the work through a telescope, communicating through his wife Emily, who had taught herself enough engineering to serve as his daily intermediary with the construction crews. He had been brought down by the same force that would kill or permanently injure 27 confirmed workers and an unknown number of others over the course of the bridge's construction. The force was compressed air, and the disease it caused was so new in 1870 that the doctors treating its victims had no name for it yet. They called it caisson disease. The workers called it the bends. This is the story of how Americans built the Brooklyn Bridge without safety equipment, without the knowledge of what compressed air did to the human body, and without a system that assigned any particular value to the lives of the men who went into the caissons to do it. The East River in 1869 was not a river in the geological sense. It is a tidal strait, a channel connecting Upper New York Bay to Long Island Sound, running between Manhattan and Brooklyn and carrying the full tidal exchange of the harbour twice a day. The depth at the bridge site ran between 78 and 95 feet at low tide, with a riverbed of soft mud over sand over bedrock that lay at varying depths below the mud. A suspension bridge of the span John Roebling had designed required towers founded on bedrock. The towers would carry the cables, and the cables would carry the roadway, and the roadway would carry the traffic, and the entire load path ran through the towers to the bedrock below. There was no alternative to bedrock. Wood pilings driven into the mud would not hold. Concrete footings placed on the mud surface would sink. Only bedrock provided the stable foundation that a structure of this weight and span required. The bedrock was between 40 and 78 feet below the riverbed, depending on the location. Getting down to it through the mud and sand and the tidal water of the East River required a method that had been developed in Europe in the preceding decades, and that was still new enough in 1869 that no American engineer had used it on a project of this scale. The method was the pneumatic caisson. A caisson was a large box, open at the bottom and sealed at the top, lowered to the riverbed and pressurized with compressed air to keep the water out of the working space inside. Workers entered through an airlock, a small chamber where the pressure was gradually equalized before the door to the working space was opened. Inside, under compressed air, they excavated the mud and sand from the riverbed, passing the material out through water locks and allowing the caisson to sink gradually as the material beneath it was removed. When the caisson reached bedrock, it was filled with concrete and became the permanent foundation for the tower above it. The principle was sound. The physics were straightforward. The problem was that in 1869, nobody understood what compressed air did to the human body when a person was exposed to it for extended periods and then returned to normal atmospheric pressure too quickly. What it did, as the workers in the Brooklyn caissons would demonstrate at a cost that the project's physicians would spend years trying to understand, was force nitrogen from the breathing air into solution in the blood and tissues under the elevated pressure, and then cause that nitrogen to come out of solution as bubbles when the pressure was reduced on the way out of the airlock. The bubbles formed in joints, in muscles, in the spinal cord, in the brain. The symptoms ranged from pain in the joints severe enough to force a man to double over to paralysis to death. The depth of the Brooklyn caissons required working pressures of approximately 2 atmospheres at the deepest point of excavation. At 2 atmospheres of pressure, a man who spent 2 hours in the working chamber and then ascended through the airlock in the standard 5 to 10 minutes that the project's procedures specified was not decompressing safely. He was decompressing in a fraction of the time his body needed to release the dissolved nitrogen safely. Nobody knew this in 1870. The relationship between compressed air exposure, decompression time, and the onset of the bends would not be understood scientifically until the early 20th century, when John Scott Haldane published his decompression tables in 1908, based on research that the Brooklyn Bridge deaths had helped motivate. The workers who went into the caissons in 1870 and 1871 were going in without that knowledge, and so were the physicians who monitored them and the engineers who set the decompression procedures. The Brooklyn caisson on the Brooklyn side of the river was constructed in Brooklyn and launched in May of 1870. It was made of yellow pine, 9 feet thick at the top, sheathed in iron plate on its exterior surfaces, and measured 172 feet by 102 feet at the base. The working chamber inside was 9.5 feet high, enough for a man to stand upright. The roof of the chamber was massive enough to carry the weight of the masonry tower that would be built on top of it as it sank. The first workers entered the Brooklyn caisson in the late spring of 1870. They worked in shifts, typically 2 hours in the chamber followed by the standard decompression, and a rest period on the surface. The work inside was excavating mud and boulders from the riverbed by hand, using shovels and picks in conditions that were described by contemporary accounts as uniquely unpleasant even by the standards of 19th century construction labour. The compressed air made sounds louder. The candles that provided the primary lighting in the chamber burned with an unusual brightness. The air was humid and difficult to breathe at the elevated pressure. The temperature was higher than on the surface. The mud being excavated smelled of the organic material it contained, and the confined space of the caisson concentrated that smell. Men worked in these conditions for 2-hour shifts, passed their excavated material out through the water locks, and came up through the airlock to the surface. The first cases of caisson disease appeared within weeks of the Brooklyn caisson going into operation. Workers began reporting joint pain, particularly in the knees and hips, after their shifts. Some could barely walk after ascending from the chamber. A few were carried from the airlock to the surface facilities where the project's medical staff was stationed. The project physician, Andrew Smith, kept records of the cases he treated. Those records were later published in the Transactions of the American Neurological Association in 1873, and they constitute one of the most detailed early accounts of decompression sickness in the medical literature. Smith treated over 100 workers for caisson disease symptoms during the construction of the Brooklyn caisson, and he was honest in his published account about the limits of his understanding of what was causing the condition and what could be done about it. What could be done by 1870 was almost nothing. The standard treatment was rest and the application of heat, which had some benefit for the joint pain cases. For the more severe cases involving neurological symptoms, paralysis, or cardiovascular collapse, there was no effective intervention. A man who came out of the caisson with the bends in 1870 and was experiencing paralysis, or had lost the use of his legs, was a man who would most likely keep those symptoms for the rest of his life. The confirmed death toll from caisson disease during the construction of the Brooklyn Bridge is 3 men on the Brooklyn side caisson and an additional number on the New York side caisson, where the depth was greater and the pressures higher. The total confirmed caisson disease deaths are recorded in the project's official records at approximately 20 to 27, depending on how cases are attributed. The unofficial toll was higher because workers who developed symptoms after leaving the project, who died weeks or months after their last shift in the caisson, from conditions that a modern physician would recognize as complications of severe decompression sickness, were not always connected to the caisson work in their death records. Washington Roebling entered the Brooklyn caisson himself on multiple occasions to inspect the work. He spent extended time in the pressurized working space and ascended too quickly, as everyone did, because nobody knew that ascending quickly was dangerous. By the time the Brooklyn caisson reached bedrock in January of 1871 and was filled with concrete, Roebling had developed symptoms that would not be recognized as caisson disease for years. The New York caisson, which went into operation on the Manhattan side in the fall of 1871, required working pressures even higher than the Brooklyn caisson because the bedrock on the Manhattan side was deeper. Roebling spent time in the New York caisson as well, continuing to accumulate nitrogen in his tissues through repeated exposures, until a severe attack in the spring of 1872 left him partially paralyzed, with chronic pain in his joints and a sensitivity to light and noise that made normal activity impossible. He was 35 years old. He directed the remainder of the construction from his house in Brooklyn Heights. The window from which he watched the work through his telescope is still in the building. He lived until 1926, dying at the age of 89, having outlived every other principal figure connected to the bridge's construction by decades. His body had adapted to the damage as much as a body can adapt to that kind of insult, but the adaptation was partial. He was in chronic pain for the rest of his life. The workers who suffered without his resources, without a house in Brooklyn Heights, and a wife who could manage the communication that kept him employed and directing the project, had no comparable support. A labourer who came out of the caisson unable to walk and who had no savings, no employer sick pay, and no workers' compensation system to appeal to, was a labourer who had exhausted his earning capacity and had the resources of 19th century charity to sustain him, which is to say, in most cases, very little. The names of the workers who died or were permanently disabled in the caissons are in the project records and in the death registers of Kings County and New York County for the relevant years. They are not in the bridge's official history in any prominent way, because the bridge's official history was written as a story of engineering achievement, and the cost of that achievement in human terms was not the story the achievement sponsors wanted to tell. The wire spinning, which began after the caissons were completed and the towers were rising, was a different kind of dangerous work. It was dangerous in the way that all high-elevation construction work is dangerous, the risk of falling, unmitigated by any safety equipment beyond the worker's own balance and grip. The wire for the Brooklyn Bridge cables was spun in place using a method that John Roebling had developed and used on several earlier suspension bridges. A spinning wheel carried individual wires back and forth across the span from anchorage to anchorage, laying them in parallel loops that would eventually be compacted and wrapped into the four main cables. The spinning wheel ran on a set of guide cables that were strung across the river before the main cable spinning began. A man working on the guide cables, or on the early strands of the main cables, was working on a wire rope approximately 2 inches in diameter, spanning more than 1,000 feet above a tidal river, with no net below and no harness attached to anything. He walked the cable the way a tightrope walker walks a wire, except that a suspension cable has a distinct catenary curve, meaning it runs down from the tower and then up again to the opposite tower, and walking its length meant descending a steep grade from the tower top, reaching the midpoint several hundred feet above the water, and then ascending an equally steep grade to the opposite tower. The river was 85 feet deep at the midpoint of the span. A man who fell from the cables at midspan had a fall of approximately 135 feet to the water surface. At that height, the water surface is not significantly softer than the ground. A fall of 135 feet is not a survivable accident by any reasonable definition. There was no rescue equipment staged on the river below the construction. The East River tidal current ran at several knots, and a body entering the water at that speed, after a fall of that height, was not a body that was going to be recovered quickly or in condition to benefit from rescue. The men who walked the cables during spinning operations were called wire walkers, and they were paid a premium over the standard construction wage to reflect the specific risk they were taking. The premium was not large. The project's payroll records, which are held at the Brooklyn Historical Society, show wire walkers earning between $2.50 and $3 per day during the spinning operations, compared to $2 for general construction workers and $1.50 for common labourers. 50 cents per day was the market price for the risk of falling 135 feet into the East River. The wire spinners who worked the Brooklyn Bridge cables were drawn primarily from the community of riggers and iron workers who had experience with elevated work on ships, on cranes, and on earlier bridge projects. They were men who had a demonstrated tolerance for height and for the specific kind of focused attention that working on an unsupported cable requires. They could not be startled. They could not look down at the wrong moment. They could not allow a gust of wind to shift their balance before they had compensated for it. The wind over the East River in autumn and winter was not the steady, predictable wind of an open field. It was channeled and variable, accelerated by the gap between the Manhattan and Brooklyn waterfronts, capable of shifting direction and intensity within seconds. A man on the cables felt every change in the wind through the movement of the cable beneath his feet, and his response to that movement was a continuous process of adjustment that went on for the entire time he was on the cable. Frank Harris was a wire spinner who worked the Brooklyn Bridge cables during the spinning operations of 1877 and 1878. His name appears in the project payroll records at the Brooklyn Historical Society, listed at $2.75 per day. He had previously worked on the wire spinning for the Cincinnati-Covington Bridge, an earlier Roebling project, and had been recruited to the Brooklyn project because of his experience. On November 11, 1878, Harris was working on the cable at approximately the midspan position, making an adjustment to a wire that had twisted during the previous day's spinning operation. The wind came up while he was working on the twisted wire, and he lost his footing. He fell from the cable. He fell 131 feet to the East River and survived. The survival was not the product of any safety system. It was the product of the angle at which he entered the water and the specific conditions of the tidal current at that moment and a degree of physical resilience that the Brooklyn Eagle, which reported the accident the following day, described as simply astonishing. Harris was pulled from the river by a boat that had been working in the channel near the bridge site. He was taken to a hospital in Brooklyn with injuries to his back and his legs. He returned to work on the bridge within 2 months. The Brooklyn Eagle's account of the accident, published November 12, 1878, describes the fall and the rescue in the compressed factual style of 19th century accident reporting. It notes the height of the fall, the distance Harris travelled in the water before being recovered, and his condition at the hospital. It does not reflect on the absence of any safety equipment that might have prevented the fall, because in 1878 there was no framework in which the absence of safety equipment on a construction site was considered newsworthy. Safety equipment on elevated construction work did not exist as a systematic practice. There was nothing to note the absence of. The total confirmed fatality count for the Brooklyn Bridge construction is typically given as 27 in the secondary literature, a figure that has been repeated in numerous accounts of the bridge's history. The primary source documentation suggests this number is conservative. The project's own death records, which are held at the Brooklyn Historical Society alongside the payroll records, list confirmed fatalities during construction. The Kings County and New York County death registers for the relevant years contain additional entries that can be attributed to bridge construction work with varying degrees of certainty. And the caisson disease cases, where workers survived their initial episodes but died weeks or months later from complications, were not always recorded in a way that connected them to the construction work. The historian David McCullough, whose 1972 account of the Brooklyn Bridge is the most comprehensive single treatment of the project in print, reviewed the available records and concluded that the confirmed death toll was likely an undercount, with the actual number of deaths attributable to the bridge construction potentially significantly higher when the long-term caisson disease casualties are included. McCullough's account, published under the title The Great Bridge, is held in the collections of the New York Public Library, along with the primary source documents he consulted. The book traces the full 14-year construction from John Roebling's death in 1869 to the bridge's opening on May 24, 1883, and it gives more attention to the human cost of the construction than any previous account had done. The opening ceremony on May 24, 1883 was attended by President Chester Arthur, New York Governor Grover Cleveland, and an estimated crowd of several thousand people on the bridge itself, and many thousands more on the waterfronts of both cities. Washington Roebling watched from his window in Brooklyn Heights. He did not attend the ceremony. Emily Roebling was on the bridge, in the first ceremonial crossing, carrying a rooster in a basket as a symbol of victory, a gesture whose symbolic intent has been debated by historians ever since. The first public crossing of the bridge took place in the days following the opening ceremony. The bridge had been opened to pedestrians and to horse traffic, and New Yorkers crossed in large numbers in the first week. On May 30th, 6 days after the opening, a woman on the pedestrian walkway stumbled on a stairway on the Brooklyn side and screamed. The scream triggered a panic in the crowd on the bridge, and in the crush that followed, 12 people were killed and many more were injured. The bridge had been open for less than a week. The tragedy of May 30th was not a structural failure. The bridge held, the cables held, the towers held, the roadway held. What failed was the management of the crowd in the first days of operation, when the bridge's capacity to carry large numbers of pedestrians had not been tested, and when the stairway configuration that caused the initial stumble had not been modified despite the density of foot traffic. The structural integrity of the bridge was affirmed in a specific and public way the following month, when P.T. Barnum arranged to march 21 elephants from his circus across the bridge on May 17, 1884. The stunt was intended to demonstrate to a public still uncertain about the bridge's safety that the structure could carry loads far beyond any normal traffic. The elephants crossed without incident. The bridge did not flex noticeably under their combined weight. The cables that Barnum's elephants walked beneath had been strung by wire spinners working at heights above a tidal river with no safety equipment, paid $2.75 per day for a risk that had no name and no systematic mitigation. The caissons those cables were anchored to had been excavated by men working in compressed air that was slowly destroying their nervous systems in ways that the physicians treating them could document but not explain and could not prevent. John Roebling had designed the bridge and died of tetanus before it began. Washington. Roebling had directed its construction and been permanently disabled by the caissons before it was half complete. Emily Roebling had managed the communication between a paralyzed chief engineer and a construction force of several hundred men for the last decade of the project, in a role that had no precedent and no title, and that she performed without compensation beyond the continuation of her husband's employment. The bridge opened on May 24, 1883, 14 years after John Roebling's death on the Brooklyn waterfront. It is still standing. The towers that the caisson workers excavated down to bedrock rise 276 feet above the water. They are the same towers, the same masonry, that the men inside the pressurized working chambers were building the foundation for in 1870 and 1871. The limestone and granite blocks that were lowered through the caisson roof and stacked on the caisson's top platform as it sank, adding the weight that drove it into the riverbed, are still there, carrying the cables that carry the roadway that carries the traffic that crosses the East River today. The traffic volume on the Brooklyn Bridge in 2024 is approximately 100,000 vehicles and pedestrians per day. The bridge was designed for horse-drawn vehicles and pedestrians, for a traffic load that its 19th century engineers could not have precisely anticipated. It carries that modern load on cables that have been maintained, and some of which have been replaced, on towers that have not been significantly modified since their construction, on anchorages that have never moved. The Brooklyn Historical Society holds the project's payroll records, the death records, Andrew Smith's medical notes on the caisson disease cases, and a collection of construction photographs that are among the most detailed visual documentation of any major 19th century construction project in America. The photographs show the towers at various stages of construction, the cable spinning equipment, and the finished structure before the roadway was complete. They do not show the interior of the caissons because photography in a pressurized working chamber lit by candles was not possible with the equipment of 1870. What the caissons looked like from the inside is known from written accounts. Washington Roebling described them in his engineering reports. Andrew Smith described them in his medical records. Workers who survived their time in the chambers described them in the newspaper accounts that were occasionally published when a severe caisson disease case attracted journalistic attention. They described the noise, which was constant and louder than anything on the surface because compressed air transmits sound more efficiently than normal atmospheric air. They described the temperature, which was warmer than outside and humid in a way that soaked through clothing within an hour of entering. They described the smell of the mud being excavated and the candle smoke that accumulated in the sealed space. They described the physical sensation of working under elevated pressure, a slight difficulty breathing, a fullness in the ears, a tendency for cuts and minor wounds to bleed less than normal. And they described the moment of ascending through the airlock, when the pressure dropped and the joints began to ache, and the question of whether this particular shift would be the one that left a permanent mark was answered by how the body felt over the next several hours. Most shifts did not result in permanent injury. Most workers came up from the caisson with some joint discomfort that passed within a day. The distribution of outcomes was not predictable in any individual case. A worker who had ascended 20 times without serious symptoms could develop a severe episode on the 21st ascent. A worker who developed symptoms on his first exposure might have none on subsequent ones. The randomness of the outcome was one of the most disturbing features of the disease, because it offered no reliable signal that could be used to identify workers who should be removed from caisson work before the serious cases developed. The men who worked the Brooklyn caissons were Irish immigrants, predominantly the same population that filled the construction labour market in New York in the 1870s. The payroll records show names that are overwhelmingly Irish: Sullivan, Murphy, Brennan, Connolly, Flynn. A smaller number of German names appear in the skilled trades positions, the carpenters and blacksmiths who maintain the caisson equipment. The engineers and foremen are identified by name in the engineering records, but the labourers are identified in the payroll ledgers by name and rate, without any information about their circumstances or their fates after their employment ended. Patrick Cody appears in the Brooklyn caisson payroll for the period from July through November of 1870. He was paid $1.75 per day, the standard labourer rate for the period. He appears in the death register of Kings County for December 14, 1870, listed with an age of 38 and an occupation of labourer. The cause of death is recorded as paralysis. Whether his paralysis was a consequence of caisson disease sustained during his months in the Brooklyn caisson is not stated in the death register. The death register did not make that connection, because in December of 1870, the medical understanding of caisson disease was not sufficient to make the connection reliable. The disease was being documented by Andrew Smith, but it had not yet been named, and the mechanism by which compressed air work caused neurological damage was not understood. Patrick Cody is one name in a payroll ledger and one name in a death register, connected by an interval of 5 months and a cause of death that is consistent with severe caisson disease, but that the records of 1870 did not officially attribute to his work in the caisson. He may have been one of the bridge's casualties. The records do not say so definitively. They say only that he worked in the caisson from July through November and died of paralysis in December. The cable spinning that followed the caisson work was the most visible phase of the construction, and it is the phase that the construction photographs most dramatically document. A photograph taken from the Manhattan Tower in 1877, held at the Brooklyn Historical Society, shows the cable spinning equipment in operation. The spinning wheel on its guide cable, the wires laid in parallel loops across the span, the scaffolding on the tower top where the wire walkers worked. In the distance, the Brooklyn waterfront and the city beyond it. Below, the East River with its traffic of ferries and barges and sailing vessels. In the foreground of the photograph, a man is standing on the top of the Manhattan Tower. He's not identified in the photograph's caption. He's standing on a surface roughly the size of a large dining table, 276 feet above the East River, with nothing around him except the cable equipment and the open air over the river and the city. He is not wearing a harness. There is no railing visible around the platform he's standing on. He is standing in the way that a person stands in a comfortable, familiar location, with no particular tension visible in his posture. He had been up there before. He would go up again after the photograph was taken. It was his job. The bridge opened 14 years after John Roebling died on the Brooklyn waterfront. It has been carrying traffic for 140 years since its opening. The towers stand on the foundations that Patrick Cody and the men who worked alongside him excavated from the riverbed of the East River in the summer and fall of 1870, under 2 atmospheres of compressed air, for $1.75 per day. The caissons are still under the river. They are filled with concrete now, the permanent foundation of the towers above them, exactly as they were designed to be. The water locks and the airlocks that the workers use to enter and exit the pressurized chambers have been sealed for 150 years. The working chambers themselves, the 9.5-foot high spaces where several hundred men excavated the riverbed by hand, in the summer of 1870, are filled with concrete and will remain filled with concrete as long as the towers stand. The men who worked in them are in the payroll ledgers at the Brooklyn Historical Society. Some of them are in the death registers of Kings County and New York County. Some of them are in Andrew Smith's medical notes, identified by symptom and outcome, sometimes by name. The bridge stands on what they did. Washington Roebling watched the opening ceremony from his window in Brooklyn Heights. He had directed the final 11 years of construction from that window, through a telescope in chronic pain, communicating through his wife because his own voice and presence were not available to the project in any direct way. He lived until 1926. He saw the automobile replace the horse on the bridge's roadway. He saw the bridge that had been the longest suspension span in the world become one of many. He saw the city that had been growing when the bridge was built become the largest city in the world. He did not often speak publicly about the bridge in his later years. When he did, his accounts were engineering accounts, focused on the technical problems and their solutions, the human cost of the construction. The men in the caissons, the men on the cables, the men in the death registers was not something he addressed directly in the accounts that survive. It was not something anyone was asking him to address. The bridge is what it built. The men who built it are in the records, if the records survived, and mostly not anywhere else. John Roebling died before it started. Patrick Cody died while it was being built. Washington. Roebling watched it open from a window. Emily Roebling crossed it first. The bridge is still there. The wire-spinning phase of the Brooklyn Bridge construction lasted from 1877 to 1879, 2 years of continuous operation that laid the 4 main cables that carry the bridge's roadway. Each cable consists of approximately 5,300 individual steel wires, each wire approximately 1/16 of an inch in diameter, bundled and compacted into a cylinder roughly 15.5 inches across. The total length of wire in the 4 cables, if it were laid end-to-end, would exceed 14,000 miles. Every inch of that wire was carried across the East River on the spinning wheel, loop by loop, by a process that required the constant attention of the men operating the equipment and the men stationed on the towers and at the anchorages to monitor the tension and alignment of each wire as it was laid. The wire itself was a point of controversy during the construction that had significant consequences for one of the project's principal figures. The wire contractor was a man named J. Lloyd Hay, who had submitted the lowest bid for supplying the wire and whose contract specified wire of a particular quality and tensile strength. During the spinning operations, the bridge's engineers discovered that some of the wire being supplied did not meet the contract specifications, that Hay had been substituting inferior wire for a portion of the deliveries and using the savings as profit. The amount of inferior wire incorporated into the cables before the substitution was discovered was estimated at approximately 5 to 10% of the total, depending on which engineering estimate is used. The inferior wire was not removed and replaced, because by the time the substitution was definitively confirmed, the cables were partially complete and the disruption and cost of removal was considered prohibitive. Instead, the cables were redesigned with an additional safety factor, increasing the number of wires per cable to compensate for the reduced strength of the inferior portion. Hay's fraud was prosecuted. He was convicted and served a prison sentence. The additional wire added to the cables as a result of his substitution gave the final structure a higher safety factor than the original design had specified, which is one of the reasons the bridge has carried loads far exceeding its original design parameters for more than a century without structural failure. The story is a specific kind of irony that the period produced with some regularity, a fraud that was discovered, prosecuted and corrected in a way that made the final product stronger than it would have been without the fraud. The cables that Hay's wire went into have never been replaced. They have been maintained and some outer wrapping has been renewed, but the core wire of the main cables of the Brooklyn Bridge is the wire that was spun across the East River in 1877 and 1878. Some of it is the inferior wire that Hay supplied. It has been carrying the bridge's load for 145 years. The anchorages that hold the cables on the Brooklyn and Manhattan shores are massive masonry structures buried in the ground at each end of the bridge. The cables pass through the anchorage chambers and are splayed into individual strands that are attached to anchor bars embedded in the masonry. The tension in the cables, which is the force that holds the roadway up, is transferred through the anchor bars into the anchorage masonry and from there into the ground. The anchorages have never moved. The masonry has never cracked in a way that affected structural function. The anchor bars have never shown signs of failure. The design that John Roebling specified for the anchorage system, based on his experience with the Niagara Falls Suspension Bridge and the Cincinnati-Covington Bridge, proved correct for a structure larger than anything he had previously built, and for traffic loads he could not have anticipated. The men who built the anchorages were doing masonry work, laying stone blocks in a precision pattern under engineering supervision, a task that was skilled and physically demanding but that did not carry the specific risks of the caisson work or the cable work. The anchorage crews were among the most protected workers on the project, in the relative sense that 19th century construction protection allowed, which is to say they were working on the ground in a fixed location, with the material they were working with weighing tons per block but stationary rather than dynamic. The masonry crews on the towers had a different experience. The towers rose 276 feet above the water, and the masons who laid the limestone and granite blocks near the top of the towers were working on scaffolding at heights that challenged the construction methods of the period. The scaffolding was timber, built in sections as the towers rose, and it was secured to the masonry as the masonry went up. A scaffolding failure at height was a serious event, and the construction records document several such failures during the tower construction, though the records are not complete enough to attribute specific casualties definitively to scaffolding accidents versus other causes. The total construction workforce at peak activity was approximately 600 men working across both tower sites, the anchorages, the approach structures, and the cable spinning equipment. 600 men over 14 years of construction represents a very large number of individual work years, and the confirmed death toll of 27 is, in that context, a mortality rate that was considered acceptable at the time. It was considered acceptable because there was no alternative framework for evaluating it. There were no regulations governing construction site safety in New York in the 1870s. There was no workers' compensation system that would have given employers a financial incentive to reduce injuries. There was no safety engineering profession that would have systematically assessed the risks of the caisson work or the cable work and developed mitigation measures. There was no body of knowledge about what happened to the human body under compressed air, because that knowledge was being created in the Brooklyn caissons in real time by the men who were experiencing the consequences. The men who developed that knowledge were not doing so by choice. They were working in a caisson because the work paid $1.75 per day, and they needed $1.75 per day. And the caisson disease that accumulated in their joints and their nervous systems over the months of their employment was not something they had agreed to, and not something they could have anticipated in any specific way. Andrew Smith, who treated the caisson disease cases and published his account in 1873, concluded his medical report with a set of recommendations for future caisson projects. He recommended longer decompression times. He recommended limiting the duration of individual shifts in the pressurized working chamber. He recommended avoiding repeated exposures in men who had shown symptoms on previous shifts. These recommendations were based on observation, rather than on the mechanistic understanding of what compressed air did to the body, which would not come until Haldane's work 35 years later. But they were essentially correct. A caisson worker who spent more time decompressing and less time under pressure was a caisson worker who would develop fewer and less severe symptoms of the disease. The recommendations were implemented partially and inconsistently on subsequent American caisson projects. The knowledge that Smith compiled in his 1873 report was the first systematic documentation of decompression sickness in the American medical literature, and it contributed to a gradual improvement in caisson working practices over the following decades. The St. Louis Bridge caisson work of the early 1870s, which overlapped with the Brooklyn project, had its own caisson disease casualties, and the physicians who treated those cases were aware of Smith's Brooklyn work and built on it. The process by which workplace safety knowledge develops, in which each project's casualties teach the next project's engineers and physicians something that reduces the casualties of the project after that, is visible in the Brooklyn Bridge caisson records. It is not a clean or efficient process. The men in the Brooklyn caissons paid with their health, and in some cases their lives, for knowledge that primarily benefited the workers who came after them on projects they would never see. This is not a unique pattern in the history of industrial safety. It is the pattern. Every improvement in workplace safety in the 19th and early 20th centuries was preceded by the deaths and injuries that made the improvement necessary, and the pace of improvement was set by the pace at which the deaths accumulated to a level that demanded a response, not by any proactive commitment to worker protection. The Brooklyn Bridge was not unusual in this respect. It was typical. What makes it historically significant in the context of workplace safety is the quality of the documentation that Andrew Smith produced and the scale of the caisson disease problem, which was large enough and visible enough to generate a medical literature that influenced subsequent practice. The workers whose experience produced that literature are named in Smith's records and in the project payroll records. Their names are accessible to researchers who know where to look for them. They are not in the Bridge's official commemorations, which list the Roebling family and the political figures who authorized and celebrated the construction, but not the 600 men who did the work over 14 years. The bridge opened on May 24, 1883. The opening ceremony was attended by the President of the United States. The bridge was described in the newspapers of both cities as a triumph of American engineering and a monument to the century's progress. Both descriptions were accurate. The monument was built on the excavated bedrock of the East River riverbed by men working in compressed air that was slowly damaging their nervous systems for $1.75 per day. The bedrock is still there. The men are in the records, most of them, if the records are consulted. The bridge is still there. That is what it cost. That is what it is. Emily Roebling's role in the construction of the Brooklyn Bridge is documented in the engineering records, in Washington Roebling's correspondence, and in the contemporary newspaper accounts that occasionally noted her presence at the construction site and her role as intermediary between the chief engineer and the project staff. What the documentation does not fully capture is the degree to which she was, in functional terms, managing a major public works project from the outside, while her husband managed it from his window, in a period when women did not hold engineering positions and were not expected to have engineering knowledge. She had taught herself engineering mathematics, structural mechanics, and the specific technical vocabulary of cable suspension bridge construction in the years after Washington's collapse, working from the textbooks and engineering manuals that were available to her, supplemented by conversations with her husband conducted when his condition allowed, and by the practical education of visiting the construction site regularly and observing what was being done. The Roebling engineering correspondence, held at the Rutgers University Special Collections, includes letters in Emily's handwriting that address technical questions in a way that demonstrates genuine understanding of the engineering problems involved. She was not simply transcribing her husband's instructions. She was engaging with the material at a level that allowed her to identify when a question required further consultation with Washington versus when she could resolve it from her own understanding. Her crossing of the bridge in the first ceremonial passage on May 24, 1883, with the rooster in the basket, was not a ceremonial gesture unconnected to her role in the construction. She had earned that crossing in a way that the politicians and dignitaries on the bridge that day had not, and the specific image of the rooster, a symbol of victory in the tradition of the time, was her statement of that fact in the most public possible context. She did not speak at the opening ceremony. No woman spoke. The speeches were given by the men who had authorized and celebrated the project, and the men who had designed it and built it were represented by Washington Roebling's absence and by the telegram he sent from Brooklyn Heights, which was read aloud. Emily Roebling lived until 1903, dying of cancer at the age of 59. She left an estate that included a law degree from the New York University School of Law, which she had earned in 1899, making her one of the first women to receive a law degree from that institution. She had gone to law school at 55 years old, 20 years after the bridge opened. The bridge that she had helped bring to completion had been open for 20 years when she received her law degree. It was carrying 100,000 people per day. It was no longer the longest suspension bridge in the world. It was still standing. Washington Roebling outlived her by 23 years. He died in 1926. 43 years after the bridge opened, having spent those 4 decades watching the structure he had directed become one of the most recognizable objects in the American landscape. His engineering report on the construction of the Brooklyn Bridge, submitted to the Board of Trustees upon the bridge's completion, is a document of unusual candor. He discusses the caisson disease problem in terms that acknowledge both the severity of his own case and the inadequacy of the medical response available at the time. He documents the wire fraud and the engineering decision to add supplementary wire rather than remove the inferior material. He records the deaths during construction in a section that is brief but that includes more specific attribution than the official death toll suggests, noting cases where he believed the cause of death was related to the construction work, even when that relationship was not formally established. The report is held at the Rutgers University Special Collections with the rest of the Roebling engineering papers. It was not widely read or cited in the decades following its submission. The popular history of the bridge was the history of the achievement, and the engineering report's candid accounting of the human cost was not the story that the popular history wanted to tell. McCullough's 1972 account changed that to a degree. The Great Bridge was the first book-length treatment of the construction that gave sustained attention to the caisson disease problem, to Washington Roebling's incapacitation, to Emily Roebling's role, and to the workers who died or were permanently injured in the caissons and on the cables. It became one of the best-selling works of American popular history of its decade, and remained in print for 50 years. The story it told, of a family that gave everything the project demanded, and of workers who gave what the project took without their consent, was a story that the audience of 1972 was ready to receive in a way that the audience of 1883 had not been. The bridge itself by 1972 was 90 years old and had been carrying motor traffic for 60 years. It had survived 2 world wars, the Depression, and the extraordinary expansion of New York City that had made it one of hundreds of bridges crossing the waterways of the metropolitan area, rather than the solitary marvel it had been in 1883. It had been designated a National Historic Landmark in 1964. Its image was one of the most reproduced in American visual culture, appearing on postcards, in paintings, in photographs, and in film from the earliest days of cinema. The workers who built it were not part of that image. The image was of towers and cables and the harbour beyond them, of a structure that seemed to have risen from the water fully formed, rather than having been assembled by 600 men over 14 years, at a cost that included 27 confirmed deaths and the permanent disability of the project's chief engineer. The photograph from 1877, the one taken from the top of the Manhattan Tower, showing the man standing on the platform 276 feet above the river, with no railing and no harness, is in the Brooklyn Historical Society's collection. It has been reproduced in several histories of the bridge, including McCullough's. The man in the photograph is not identified. He was there. The photograph proves it. Who he was, what happened to him after the photograph was taken, whether he is among the confirmed dead or among the survivors who dispersed after the construction ended and left no further trace in the available records, is not known. He was standing on the top of the Manhattan Tower in 1877, in the way that a person stands in a familiar place, with the East River 276 feet below him, and the unfinished cables running away toward Brooklyn and the city of Manhattan visible behind him, and the camera capturing a moment that he was probably not thinking about, and that has outlasted him by 147 years. The bridge is still there. He is in the photograph. That is what the record holds. The Brooklyn Bridge's structural longevity is not an accident. It is the product of several specific engineering decisions that John Roebling made in the original design, decisions that built in redundancy and safety factors beyond what the bridge's anticipated loads required. The most significant of these decisions was the choice of steel wire over iron wire for the cables. In 1869, when the bridge was being designed, steel wire was a relatively new material for suspension bridge cables. Iron wire was the established choice, and Roebling had used iron wire on his previous bridges. Steel wire was stronger per unit of cross-section, which would allow smaller cables to carry the same load. But its long-term behaviour in the corrosive environment of the New York Harbor waterfront was less well established than iron wire's behaviour. Roebling chose steel wire, accepting the uncertainty about its long-term behaviour in exchange for the strength advantage that allowed his design to achieve the span and load capacity he intended. The choice proved correct. The steel wire in the main cables, while it has required maintenance and protective treatment over the years, has retained its structural integrity for 140 years in an environment that is among the more corrosive that a bridge structure can face, with salt air, tidal humidity, and the exhaust of a century of motor traffic all working against it. The second significant decision was the use of diagonal stay cables in addition to the main suspension cables. A conventional suspension bridge carries its roadway load through vertical hangers that connect the roadway to the main cables. The main cables carry the load to the towers and from the towers to the anchorages. Roebling added a system of diagonal cables running from the towers to points along the roadway, giving the bridge a secondary load path that stiffens the structure against the oscillation that long suspension bridges are subject to in wind. The diagonal stay system was not standard practice in suspension bridge design in 1869. It was Roebling's innovation, derived from his observation of how suspension bridges behaved in wind, and his conviction that the conventional suspension system alone was not adequate for the stiffness that a long span over a busy waterway required. The diagonal stays have contributed to the Brooklyn Bridge's resistance to the wind-induced oscillation that caused the Tacoma Narrows Bridge in Washington state to collapse in 1940, 71 years after the Brooklyn Bridge was designed. The Tacoma Narrows failure, which was caused by aerodynamic flutter in a bridge design that lacked the stiffness the Brooklyn Bridge's diagonal stays provided, was studied extensively after the collapse and led to fundamental changes in suspension bridge design worldwide. Roebling's diagonal stay system, designed decades before the aerodynamic properties of suspension bridges were scientifically understood, provided the stiffness that prevented the Brooklyn Bridge from exhibiting the same vulnerability. He had arrived at the correct solution by empirical reasoning from observation of earlier bridge behaviour. without the theoretical framework that would have explained why his solution was correct. The bridge that resulted from these decisions, and from the 14 years of construction that implemented them at a cost of 27 confirmed lives and the permanent disability of its chief engineer, is a structure that has outlasted every contemporary's expectation of its useful life. In 1883, engineers estimated that a major rehabilitation of the bridge would be required within 20 to 30 years, as the wire cables reached the end of their expected service life, and the masonry towers showed the effects of the traffic loads they were carrying. The rehabilitation that was anticipated in 1883 did not occur on that schedule. The bridge required ongoing maintenance, and the cables were inspected and treated periodically, and some elements of the approach structures were modified as traffic patterns changed. But the primary structure, the towers and the cables and the anchorages, has required no fundamental reconstruction in 140 years of service. That durability is the final measure of what the construction achieved, and it is worth stating alongside the death toll and the caisson disease casualty list, and the paralysis of Washington Roebling, because both things are true simultaneously, and neither cancels the other. The bridge is still standing because the men who built it correctly, at a cost that was borne by the men in the caissons and on the cables, and not by the men who commissioned and celebrated the structure. The man on the Manhattan Tower in the 1877 photograph was doing his job on a platform 276 feet above the river, with no safety equipment, for $2.75 per day. Patrick Cody was excavating the East River riverbed in a pressurized wooden box for $1.75 per day until December of 1870, when the Kings County Death Register recorded his death from paralysis. Washington Roebling was watching the construction through a telescope from a window in Brooklyn Heights, in chronic pain, directing a project that had taken his ability to stand on its site. Emily Roebling was crossing the bridge on the day it opened, with a rooster in a basket, having spent a decade as the functional intermediary between a paralyzed engineer and a construction force of 600 men. John Roebling had been dead for 14 years. The bridge was open. The East River ran beneath it, the same tidal strait it had always been, carrying the same harbour traffic it had carried before the first caisson was lowered, and would carry long after the last maintenance crew had finished its work and moved on. The towers stood on the bedrock that the caisson workers had reached. The cables ran from anchorage to anchorage on the wire that the spinners had strung loop by loop across the span. The roadway carried the traffic that the men who commissioned it had promised it would carry. 100,000 people per day cross the Brooklyn Bridge now. They cross in cars and on foot and on bicycles, over the same East River, on the same structure, anchored to the same bedrock that the men in the Brooklyn caisson reached in January of 1871, after 8 months of working in compressed air for $1.75 a day. The bridge is what it cost. The bridge is also what it is. Both things are true. Both things are still there.